Hello, my name is Dan Maguire and I am a second year PhD student at the University of Strathclyde in the UK under the supervision of Dr. Yashar Mishveg. So to give you a bit of an introduction to the paper, firstly we understand that the primary goal of an information retrieval system is the fulfillment of a searcher's information need. Many impactful works have attempted to define the concept of information need, for example, Taylor's question negotiation process, anomalous state of knowledge model, and Wilson's information seeking behaviour. To understand an information need, these works employ techniques such as user-system interactions, self-reflective notes, In response to these limitations, a new field of research has begun to investigate the use of neurological activity to directly and implicitly assess the development of information needs. This intersection of neuroscience and information retrieval is often referred to as neurosearch. Prior works have investigated the tangible representation of information needs by examining the neural correlates within participants. For example, the works of Mishveg et al. Have employed functional magnetic resonance imaging, in other words fMRI, These works have provided compelling evidence to the existence and expression of information needs within participants' neurological activity. However, the use of fMRI for this analysis presents several limitations. Firstly, the hardware of fMRI device is physically large and monetarily costly. It requires the subject to lie supine within the central bore of the apparatus while maintaining stillness. Despite its fine spatial resolution, fMRI exhibits suboptimal temporal resolution, with each measurement taking a duration of 2 seconds. This is then further compounded by the blood oxygenation Unlike prior fMRI studies that demonstrate the ability to predict the realisation of information need, it is still unknown if the realisation of an information need can be predicted in real time through the use of EEG data. From this hypothesis, we formulate the following 4 research questions for our paper. Firstly, is it possible to predict the realisation? Subjects were recruited by the University of Strathclyde. They received no monetary payments but were instead eligible for academic credits. The subjects' composition consisted of 13 females and 1 male, with an age range between 18 and 39 years old, with a mean age of 23 years with a standard deviation of 6.5 years. In order to capture the EEG data, we utilised a 40 electrode neuroscan limited system with a 1020 cap layout, sampled at a frequency rate of 500 Hz. The question and answer dataset was composed of the general knowledge questions taken from the TREC 2001 and the BK Norms database. 2 assessors then separately evaluated the question difficulty with a Cohen's kappa of 0.61. A subset of 120 questions was then selected and both annotators agreed upon their difficulties, with the difficulty of the questions being equally distributed between easy and difficult for the final dataset. Ethical permissions to conduct the study was approved by the University of Strathclyde's Ethics Committee. The tasks were conducted in a laboratory settings with all subjects meeting the inclusion criteria, which was healthy, 18 to 55 years old, fluent in English, and no prior/current neurological disorders. Before the main trial, subjects were taken through a practice example consisting of 5 questions not including the main trial, which was repeated until the subjects were comfortable. Now I'll take you through an example of our procedure run. The trial began by viewing a fixation cross in the middle of the screen for a duration of 2000 milliseconds, indicating the location of the next stimuli on screen. This was done to minimize eye movements on the screen. The participants then viewed a sequential presentation of the query randomly selected from the dataset. In this example, our query is, when is Independence Day? Each word within the question was displayed for 800 milliseconds on screen at a time. Within the steps, the subject processed the information as it was presented word by word. Following the presentation of all the words within the question, the subjects were presented with a now fully displayed question and 3 on-screen choices associated with the answer. They were then requested to select the correct answer or the option I do not know. If the subjects correctly or incorrectly answered the question, the answer would be displayed on screen. We labelled this as no need to search, where the trial then terminated and moved on to the next question if there were questions remaining. However, if the subject selected I do not know, they were then presented with 2 more options, whether they wanted to search, so this would be a need to search, or they had no need to search. During the recording of EEG data, it's common for noise artifacts to embed themselves within the data. These artifacts are often a result of electrical activations associated with muscle movement by the participants, as well as electrical interference from nearby devices or power outlets. These artifacts can hinder classification accuracy and distort the final results. As such, we apply a series of processing methods to reduce the effect of these artifacts. For this work, we apply bandpass filtering between the ranges of 0.5 up to 50 Hz. This range is commonly adopted as research has shown that the brain's recorded electrical activity falls within this spectrum, and so anything out with this range could be considered noise. Re-referencing was also applied, and this is done by establishing a reference point by aggregating the activity measured from across from all of the electrodes. The objective is to capture any noise or interference impacting all electrodes uniformly. This reference is then subtracted per electrode. For this study, we also extracted a commonly used coarse set of features for EEG signals in order to evaluate which combination is ideal for information need prediction. Each feature was extracted per electrode, in our case 40 electrodes, across 4 discrete wavelengths, these being delta, theta, alpha, beta, and gamma. Features were extracted across each of the 800 millisecond blocks where the query's words were presented on screen. And for this study, the feature sets that we extract are as follows: mean, standard deviation, kurtosis, curve length, number of peaks, and average nonlinear energy. To address each of the research questions, we designed the following experiment scenarios. Firstly, generalized and personalized. This is meant to address research question 2. During training, 2 methods are devised. The first approach samples relating to information need and non-information need from every subject were combined into a single dataset that would then be passed on to the model for training. This being generalized training, assessing how well our classifier can discern information need across all subjects, as research has been shown that EEG data is heavily subject dependent. The second approach maintained the information need and non-information need EEG data at subject level, allowing us to assess the variability of subject performance for information need prediction. Secondly, to address research question 3, we adjusted the size of the question segments, in our case words, used by our classifier. This modification involved implementing an expanding window starting from the onset of the subject's search decision, i.e. no need to search or need to search, and working its way backwards to the query. On average, each question comprised 7 segments, encompassing both the words and the responses, with the minimum segment count being 4, whilst the maximum was 16. Within this work, we explore 4 distinct window sizes: 2, 4, 8, and 16. Lastly, to address research question 4, we explore the optimal combinations of features commonly extracted for EEG classification to determine which combination may be best suited for information need prediction. We extract 7 key features, which we discussed in the last slide, which are then used to generate an exhaustive list of all possible combinations, resulting in a total number of combinations equal to 127. For this work, we incorporated each of the experimental conditions into a training loop, where generalised and personalised were separated, where each would iterate through every possible feature combination and window size. For this study, we utilised the following predictive models: support vector machine, random forest classifier, and AdaBoost. Each have demonstrated their success in previous research for EEG classification tasks. Preliminary investigations made use of more complex recurrent neural networks. However, their performance was suboptimal given the limited quantity of available data. For this study, we utilised the following evaluation and metrics. Each of the models was evaluated using a k-fold cross-validation with a k size equal to 5. With each fold, the models returned accuracy, precision, and recall. Since no prior works existed to compare our methods to, we take the random probability of the classification between the IN, or information need prediction, as the baseline, this being 50%. Reviewing the results produced in both generalised and personalised conditions, we can see that prediction of the realisation of information need is possible, as every model in Table 1 and Table 2 was able to achieve an accuracy score above that of the random classification baseline, which was 50%, with the lowest reported accuracy score being the random forest classifier with an accuracy of 68.9%, and the highest being the AdaBoost model with a score of 90.1%, as seen in Table 2. These results demonstrate that EEG data is capable of achieving greater generalised and personalised accuracy performance for the prediction of information need than alternative neuroimaging techniques such as fMRI. By comparing the performance of the generalised and personalised models, it can be observed that the personalised approach achieves a higher overall prediction accuracy, evidenced by the AdaBoost model in Table 2. When trained using the personalised method, the random forest, SVM, and AdaBoost models model accuracy on average across window sizes increases over its generalised counterparts by 1.4, 4.2, and 13% respectively. However, this increased accuracy also comes with the increased standard deviation, with the personalised random forest, support vector machine, and AdaBoost models on average across window sizes having higher standard deviation of 19.3%, 21.8% and 22.4% respectively than generalised models. Regarding research question 3, the results presented in Table 1 and Table 2 are in contrast to each other. In the generalised condition in Table 1, we observe that all models achieve their peak performance when the window size is set to 2, with the random forest, SVM, and AdaBoost models achieving an accuracy of 73.5%, 69.7%, and 70.6% respectively. Conversely, in the personalised results in Table 2, we observe that the window size of 16 achieves the highest performance, with the random forest, AdaBoost, and support vector machine models achieving their highest performance of 76.6% and 90.1%. As the window sizes increase from 2 up to 16, the random forest and AdaBoost models' accuracy increases by 7.7% and 16.2% respectively, with the exception of the SVM model, which follows the same trend as the generalised models. The results produced by generalised approach suggest that the distinct EEG patterns associated with the realisation of an information need may be more strongly concentrated immediately after the subject concludes their review of the question. This might be indicative of a universal or commonly shared cognitive response that occurs promptly after the comprehension of a query. Lastly, addressing research question 4, we can observe that the best performing feature is the mean value taken from the EEG segments, as it appeared in every single best performing combination at each window size for both generalised and personalised training in Tables 1 and 2. However, a large subset of key features see substantial use across both training conditions. For generalised condition, the following features are listed in order of occurrence, with curve length appearing in 7 optimal combinations, average energy in 5 combinations, standard deviation in 4, number of peaks in 2, and skewness in 1. Similarly, for personalised, this consists of average energy, which appears in 4, curve length in 3, kurtosis in 2, and standard deviation in 1. Our results indicate that these features are strong performers in the prediction of the realisation of information need. In conclusion, we show that using EEG data, we were able to predict the realisation of information need with accuracies up to 90.1%. We're the first to ever achieve this using EEG data, demonstrating its viability as an indicator of information need. We achieve accuracies higher than any other previously shown neuroimaging techniques such as fMRI or MEG, and we provide insights into future research and information retrieval applications when considering generalized versus personalized systems. And lastly, we outline the optimal combination EEG features as well as window links.